Hi. In this video we're going to be looking at the runtime of binary search, along with looking at the iterative version of it. So here's our binary search algorithm again. We look in the middle. If it's not found, then we either look in the lower half or the upper half. So what's our occurrence relation for the worst case runtime? Well, the worst case is if we don't find an element. So we're going to look at t of n is equal to t of roughly n over 2 plus c. We have a floor there of n over 2. Because if n is odd, like let's say there are 5 elements, then the question is how big is the problem size on the next call. So if we have 5 elements, we're going to either end up looking in the upper half of the array, those 2 elements, or the lower half of the array, those 2 elements, because we skipped the midpoint. We already checked that one. Plus some constant amount of work to add together, calculate the midpoint, as well as checking the midpoint against the key. And then our base case is when we have an empty array, and that's just a constant amount of time to check. So what's the runtime look like? We got our original size n, and we're going to break it down, n over 2, n over 4, all the way down. How many of these problems are there? Well, if we're cutting something in 2 over and over again, it's going to take log base 2 such iterations until we get down to 1. So the total here is actually log base 2 of n plus 1. The amount of work we're doing is c. So at each level, we're doing c work. So the total amount of work, if we sum it, is just the sum from I equals 0 to log base 2 of n of c. That is just log base 2 of n plus 1. That is log base 2 of n, that quantity, plus 1 times c. And that is just theta of log base 2 of n. Or really what we'd normally say is theta of log n, because the base doesn't matter. That's just a constant multiplicative factor. All right, what's the iterative version look like? The iterative version has the same parameters, low, high, and key, and we have a while loop that goes through similar to the base case. So in the base case of the recursive version, we were stopping if high is less than low. Here we have a while loop where the while loop stops if high is less than low. We calculate the midpoint, and then, again, check the key. If it matches the element at the midpoint, we return the midpoint. Otherwise, if the key is less than the element, we know we're in the first half of the array, and so instead of making a new recursive call, like we did in the recursive version, we have the original array, and we want to look at the first half of it, so we're going to change the value of high. And then it'll be mid minus 1, because we already checked mid. Otherwise, we want to look in the upper half of the array, so we move low up. If we reach the end of the while loop, that is, if we drop out of the while loop because high is less than low, that meant we have nothing more to search. We have an empty array. And therefore, we didn't find the element in the array. We're going to return low minus 1. So the same result as the recursive version. The difference is we won't be using the stack space that the recursive version uses. You remember we talked 2 videos ago about this real-life example where we had 5 languages and we were translating words between any 2 of those languages. The way we had that represented was parallel arrays, so that at any given index, each of the elements of the arrays represented words that were the same in all those languages. So for instance, chair in English is at index 2, and in Spanish that's silla, and in Italian it's sedia. The problem was it took a long time to look, right? We had 50,000 elements in our arrays, and it took like 10 seconds for searching, because we had to really search through all of them. If it wasn't there, on average, half of them, which is 25,000. So one question might be, why didn't we use a sorted array? Right? You can imagine, for instance, sorting these arrays. Here they're sorted. The good part is it's easy to find a particular word in a particular language. So I can find house in English, for instance, and find what index that is at very quickly using a binary search. The problem is I no longer have this correspondence because the order of the words that are sorted in English is different from the order of the words sorted in Spanish. So if I look at chair, for instance, in English, it no longer maps to silla. So instead, if I look at chair, it maps to casa. So although we can find a particular word in our source language, we don't know the corresponding word in the target language. So the solution was to try and find some way we could do sorting and yet still preserve this relationship where everything at an index meant really the same translated word. And the way to do that was an augmented array, or set of arrays. So what we really did was keep this augmented arrays which were pointers back into the original arrays in sorted order. Okay, so we're having kind of a level of indirection here. So if I look at English, for example, the order of the words in English is chair, house, pimple. Well, what order is that in the original array? It is first element 2, and then element 1, and then element 3. So if you want to do a binary search, you can use this sorted array. But whenever you want to look at what's the element that is in that represented sorted array, so for instance, if we looked at the middle element, so which in the sorted array is 2, it has the value 1, and that says go find house. So we basically say house is sort of at element 2, and chair is at element 1, and pimple is at element 3. The Spanish, of course, has different mapping. So in Spanish, the first sorted word happens to be the first word in the array. The second sorted word is the third word in the Spanish array, and the third sorted word, silla, is the second element. So what happened when we ran this? Well, what happened, we had a space-time trade-off, right? We had to pay extra space. And there were, of course, not only just English and Spanish sorted, but also French, Italian, and German. So 5 arrays, extra arrays. Each array had 50,000 entries in it. And what was the size of each element of the array? Well, it represented a number from 1 to 50,000. That can be represented in 16 bits, which is 2 bytes. So we had 50,000 elements times 2 bytes. So that is 100,000 bytes. Times 5 is 500,000 bytes, so about a half a megabyte, which today is almost nothing, and even then was certainly doable 20 years ago. That's the cost we have in sort of space. What is the benefit that we get? Well, instead of having to do, let's say, 50,000 lookups in the worst case, instead we have to do log base 2 of 50,000 lookups. So log base 2 of 50,000 is about, let's see, log base 2 of 1,000 is about 10, goes 2 to the 10th equals 1024. So we have another factor of 50 to go. Log base 2 of 50 is around, let's say, 6, because I know that 2 to the 5th is equal 32, 2 to the 6th is 64. So what that means is we have 16 references we have to do to the array instead of 50,000. That's almost a factor of 1,000. So what that ended up meaning is that when the user clicked translate, instead of taking 10 seconds, it was what appeared to be instantaneous. It was well under a tenth of a second. So in summary, what we've seen is that the runtime in binary search is big theta of log n, substantially quicker than the big theta of n that linear search takes. So sorted arrays really help. In the next lesson, we're going to be looking at a more complicated application of divide and conquer, where we actually have multiple subproblems instead of just one subproblem.